So the very first type of reaction that we're going to focus on is how do we brominate? And bromination is going to be the process of adding a bromine to a molecule. And most of our brominations are going to be adding bromine to just an alkane. So we'll take a simple alkane and then find ways to add bromines to it. Now, in the next class, we're going to learn the actual mechanism behind, and we're actually going to draw arrow pushing to show how that bromine gets there. Right now, all we want to do is focus on what are the what are the big broad classes or reaction conditions for bromination, and then how do we predict the product. And then next time, we'll then focus on all the specific mechanisms. So there are going to be 4 major reactions that we're going to talk about in ways to add bromination. The nice thing about these is even though they're going to have different reaction conditions, the product that they're going to generate are all going to be the exact same. The very first one, and one of the ones that's the most common, is going to be using diatomic bromine, so Br2, and then light. Now, Br2 and light is a really good reaction in terms of textbooks. You'll see that all the time in textbooks. However, it's not the greatest in terms of like actually using. Bromine itself, Br2, is extremely corrosive. It will act if you put it in a cabinet, even if you just have like a little screw, it will corrode your screws a ton, and it'll like turn it into like this black sludge. It's a really reactive chemical, and you're able to brominate a few kind of shortfalls of using liquid bromine, and we'll call it liquid bromine a lot because it is a liquid, Br2, diatomic bromine. One issue with using liquid bromine, beyond it just being super corrosive, is it can also have a potential to overbrominate. And sometimes you can get, instead of just trying to do one bromination, sometimes you can do multiple. But that's kind of like your kind of stereotypical example that we'll do a lot with Br2 and light. Now, there are other ways in which you can initiate other than light. So HNu, which is written under the arrow, means light. And maybe I'll just kind of do another one. So this means light. There are other ways in which you can generate a reactive bromine species other than light. And those are going to be our kind of next conditions. Those are going to be using a radical generation. So one of the ones we're going to talk about has an abbreviation of AIBN. There's a big complicated structure. Also a kind of quick preview up here. There are azo compounds which have a nitrogen double bond nitrogen, and these are really good at generating radicals. So this is the structure of AIBN, which we'll talk about in our future video. AIBN is really good at generating radicals. So you can use AIBN in the presence of bromine instead of light. AIBN can use light, but a lot of times you also use heat. So heat will show with a triangle. So you can use light or heat with AIBN, and that is a radical generator. The other one that you can use is a peroxide. So you can use Br2 and a peroxide, which I'm going to call ROOR, and there's our peroxide. A peroxide is going to be a species that has 2 oxygens single bonded to each other. 2 oxygens single bonded to each other are super unstable. In your kind of bathroom, you might have hydrogen peroxide, where both of those R's are both hydrogen. So hydrogen, oxygen, oxygen, hydrogen. And if you get a cut or something, you might put it on, and it's like kind of bubbles and sizzles and stings and kills a bunch of stuff. Peroxides are super, super reactive. So they're another source of generating radicals. So you can use light, heat, or peroxides, and often with peroxide you also use heat. So those are all kinds of different conditions that you can use with bromine. The other one that you can use is a molecule that we'll also learn next time called NBS, which stands for N-bromosuccinimide. It's really good at generating radicals, especially bromine radicals. There are others. You can do N-iodo or N-chlorosuccinimide to generate chlorine or iodo radicals. But these are some of the kind of key reaction conditions that we would use. And for all of these, you will have a molecule, you will react with it, and then you'll get a bromine on it. So let's go ahead and talk about how do we predict where a bromine would go on a molecule. So underneath I have a handful of different reactions and we're going to go through and think about what would be the product for each of those reactions. So for our first one, we have a structure. It is a cyclic structure with 5 carbons. So in terms of naming, we'd call that cyclo for the cyclic structure, meth, eth, prop, bute, pent, pent being 5, and then ane because that's all single bonds. So cyclopentane could be the way in which you can name this. We see here our reaction conditions are Br2 and light. And you could replace that with any of the ones up above and you get the exact same general reaction. And in this case, that means we're going to be doing a bromination reaction. So we're going to be adding bromine to our molecule. Now, where we will add the bromine is going to be where we have the most stable reactive intermediate. And that reactive intermediate is going to be a radical. In our next set of videos, we're going to talk about how we generate that radical. But for the sake of this video, all we're going to do is we're just going to put a radical in the most stable spot possible and then put a bromine there. Now, for a structure like cyclopentane, all of your spots here have the exact same stability. Remember, when we think about stability, we're going to use that primary, secondary, tertiary, allylic, and benzylic descriptions. Here, all of your positions are secondary. They all have exactly 2 bonds to them. So there is actually no preference. So we can go in and we can put a radical on any of our spots. So I'm just going to go ahead and put a radical randomly on the spot to the right. And if that is my reactive intermediate, I'm going to end up with a bromine at that location. So in this case, if I take a cyclopentane and I react this with bromine and light, I'm going to get a bromocyclopentane. So we're going to add a bromine at our most stable spot, and in this case, it can be any spot. Now, that's a nice easy example because all of those have the same level of stability. In our next example, we don't. In our next example, we kind of have a good spread. So let's go ahead and think of our next molecule. If we wanted to name that, we have 1, 2, 3, 4, 5. So our backbone is also going to be a pentane, but we have at the 2 position a methyl, so 2-methyl pentane. At this, there's going to be a difference in terms of stability of our radicals. If I look at this position, or this position, they would all be primary. And we know that primaries are very unstable. Those only have a single bond to them. There are these 2 locations here, both which has 2 bonds, which would be secondary. And then right here in the kind of like armpit, we have what we would call a tertiary because we have 3 different bonds. Of all those different locations, that tertiary is going to be our most stable. So our key reactive intermediate is going to be putting a radical in that center. And if we have a radical in that center spot, we are then going to stick or replace that with a bromine. So here, our reaction of 2-methyl pentane will go to 2-bromo 2-methyl pentane. And for all of our brominations, all we're going to do is try to find what is our most stable spot and then stick a bromine on there. Now let's go ahead and think about our next molecule. So here, this is a 1, 2, 3, 4, 5, 6. So this is a hex. This is a hexene, E-N-E, because of the fact that we have a double bond. If we draw that hexene, we have a few different spots where we can consider stability. At the far end over here, we have a position that is primary. However, it can undergo resonance with our double bond. So that is primary plus allylic. And that allylic is a really good stabilizing. The spots where you have your double bond are not very reactive. You don't want to do a bunch of chemistry there. If I look at the other spot over here, this would be secondary and allylic compared to just a normal secondary and a normal primary at the end. So between the primary allylic and the secondary allylic, your most stable is going to be at the secondary allylic. So if you wanted to draw your product, you'd start with the exact same general structure and then put a bromine at that kind of secondary allylic position. Same thing if you would have like a benzylic. So for all of our different bromination conditions, whether you're using bromine and light, bromine and AIBN, bromine and peroxide, or NBS, what we're going to do is we're going to look at our starting material. We're going to try to find its most stable location. In many ways, if you wanted to relate this back to acid-base chemistry, you could try to find the most acidic proton. The most acidic proton is going to give you the more stable conjugate base. All of these are going to have a radical at the location of your most acidic proton. And what you're going to do is you're going to end up putting a bromine at that location. Now, the mechanism for how this bromine gets there is a lot more complicated. And in our next set of videos, we will go through and talk about the actual mechanism and how that bromine magically appears there. And it's going to be a free radical reaction that has an initiation of propagation and a termination. But right now, take your structure, find your most stable spot where you could put a radical, and then that's going to be the same location of where you're going to put your bromine.